Where we learn all about probability. We're starting with section 5.1, which is about the law of large numbers and simulations. So this first video will talk about what the law of large numbers is. The second video has examples of some simulations. So the basic idea of probability is that chance behavior, although it might be unpredictable in the short run, it has a regular and predictable pattern in the long run. And that principle dictates so many things, such as insurance rates and things like that, that maybe one person can get in an accident. That's your short run. But then if you think of the overarching, all the clients who are in that insurance company, that has a regular and predictable pattern of what they expect to spend in the long run. So the law of large numbers is the law that describes this, and it says that as we observe more and more repetitions, right? That's our replication. As we have greater replication of any chance process, the proportion of times that a specific outcome occurs is going to approach a single value. So basically, that probability from your experiment or simulation or whatever your trials will get closer and closer to the probability of the truth. Now, there is a law that some people say, like, hey, I've been playing this lottery for a long time, I'm due, or we've just had 5 boys in a row, we're due for a girl. That's a phony law. It's called the law of averages. It's different from the law of large numbers. And this is a false thinking that just because you've tossed 6 tails in a row, that the next flip of the coin is going to be heads. So we have to realize that this is not true, and we have to remember that on that next flip, it still will go back to being 50-50, a chance of tails or heads. So when you're thinking about your problems, I want you to always think in terms of long run and many, many trials, or large sample size, things like that. Don't think of one trial as influencing the result of the other trials. So here's a little example to think this sort of through. Now, athletes are often tested for the use of performance-enhancing drugs. Drug tests aren't perfect. They sometimes say that an athlete took a banned substance when that isn't the case, and that would be a false positive. Other times, the test concludes that the athlete is clean when he or she actually took a banned substance, false negative. For one commonly used drug test, the probability of a false negative, given the person is actually taking drugs, is 0.03. So let's interpret this probability as a long-run relative frequency. So long run, we could use words like many, many trials or large sample size, something like that. So if we were to perform, let's see, many, or on a large sample size, many trials of this drug test. Okay, and this is false negatives, and the person's actually taking drugs. Okay, so on people who were taking drugs, performance-enhancing drugs, we would expect approximately, I'm putting that word in because I don't want to sound like I expect exactly 0.03. I would expect around that. We would expect approximately 0.03 or 3% would result in false negatives. Okay. What is more serious error in this case? Would you rather get a false positive or a false negative? So let's think that through. A false positive that would be person not taking drugs, not drug user, right? That's what they would be. You said they were, or results said they were. Let me say results say they are. Results said they use drugs. So what'd you do? You, what'd you do? You kicked them out of the league, or you banned them from competition? Competition. Okay, then let's think about false negative. Yes, a drug user. This was not realized because you just said that they, okay, they got to compete. They continued to compete. Okay, so those are the two situations, and then we have to decide which one is worse. And in the United States, because our entire legal system is based on you're innocent until proven guilty, and we would prefer to let guilty people go free, which I agree, than lock up an innocent person. It is not right to take away from someone the right to compete in the competition when it was a mistake on our part. So this one is definitely a worse situation. And we can talk about that in class if somebody wants to think that through a little more. So does this probability say that if we test 100 athletes who are using drugs, that we will have exactly 3 false positives? If 100 athletes were tested, actually drug using, were tested, we would expect approximately 3 to be false positives, but not exactly every time. I mean, it could happen, but we expect it to be approximately, and there's that word of around that. So if it was 2, 4, we'll learn ways to figure out how far off it has to be strange. But we would not expect exactly 3 false negatives. Oh, false negatives. Sorry. Negatives. We would expect around that, but we never expect life to be perfect. Okay, so theoretical probability, which is also referred to as classical probability, and it's based on the number of times event A occurred in the sample space. So if you think of S is your sample space, if, like, for example, I was doing the days of the week, or how about, actually, let's do the vowels, then my sample space, that's brackets showing it's a set, A, E, I, O, U, and I don't know if we want to include Y in there, sometimes Y. So like that would be my sample space. So then if I wanted to say, like, what's the probability that my name begins with a, or somebody's name is going to begin with an A, if I know it's a vowel, then I could look at the number of times A occurs in my sample space over the total size of the sample space. So probability of event A would be number of times A was in sample space over total size of sample space. Then we have our empirical, also known as experimental probability. This is based on data. So the probability of that happening is going to be, probability of A is going to be the number of times A occurred in the trials over total number of trials. Okay, and so this usually involves data sets collected from either a simulation or from just observing the data in the world. Okay, and then subjective probability, like what's the probability that I'm going to do laundry tonight? That kind of can vary based on your personal belief, intuition, your opinion. What's the probability that the sun's going to rise tomorrow? It will, in my opinion. I'm going to say 1 because probabilities vary from 0 to 1. So that's going to be based on your personal belief. Somebody else might say, well, I don't think the sun's going to rise tomorrow. I put that probability at 0.9. And they wouldn't be wrong, but, well, let's hope they're wrong. but subjective is going to be based on your personal belief, and it can vary widely from person to person. And some people might be right with their value, and some people might be wrong. So what are some values that are not probabilities? Well, pi is not a probability. Why? There's 2 reasons why. Irrational numbers are not probabilities. Also, pi is greater than 1. So any number greater than 1, and also any number less than 0. So you can't have any negatives. You couldn't have something like 5 over 2. That's greater than 1. That could not be. So these are all examples of things that could not be probabilities. Let's throw out some other E and I, some other weird numbers in math. So if you ever get a value over 1, you know you don't have a probability. All right, so this activity we'll do in class. So save this page and the next page for when you're in class, and we will look at that in class. Next video will cover simulations.